Okay, let's look at the induction equations. Basically, the induction equation will derive from two Maxwell's equations, here and here, and Ohm's law. So this equation, and this equation. So start with one of the Maxwell's equation, and we plug J into the Ohm's law, generalized Ohm's law. We have this, and put anything have magnetic field on the left hand side, electric field on the right hand side. We have this, and we multiply do a curl on both sides, and we end up with this. So this, we can use another Maxwell's equation to make this whole equation only an expression of magnetic field. So basically, you substitute this with that. We have this, and then of course this thing we'll be using so many times now. It's like a vector calculus identity. You just need to use this, and we know that another Maxwell's equation gives us this equal to 0. Then we tidy it up, where we have this expression. Up to now, of course, this have a low frequency approximation, inherently have low frequency approximation in it, because there's high frequency correction, as you remember from the derivation that I had. And so this term has omega, basically ddt squared. It's in the order of frequency squared. So it will be neglected for low frequency limit. Just to illustrate the point, you can compare those two terms. So this term can be in the ordering, in the terms of ordering, then this will be 1 over L squared. So this term will have the order of omega squared L squared over C squared. So that will be V naught squared over C squared, which is for non-relativistic scenarios we will have this will be less than 1. So this term will be neglected. Then we're left with the final equation, induction equation. Of course, this only works for low frequency. As you know, all the approximation here, the approximation, and here, approximation intrinsically tells us that we're dealing with low frequency. So this is, those three terms have relatively intuitive physical understanding. So this is a changing of magnetic field with respect to time. This is pretty much coupling with the fluid. You can think the fluid motion has a basically coupling with a magnetic field. So if it's not strictly aligned, then it will create some non-zero effect. And this acting like a diffusive term, you can think of the changing of magnetic geometry with finite conductivity. Then the particle will slowly diffuse to the direction where it has a lower, essentially lower potential. So it will be diffused out due to the magnetic geometry. And this coupling is in the order of V naught over tau. Tau will be in tau is the order of L over V naught. As you can see, this is 1 over L, this is V naught. And diffusive term will have V naught over tau d. Tau d is in the order of L squared 4 pi over eta c squared. So as you can see, with perfect conducting scenario, then this term will be 0, because it will just all the particle is essentially just following the magnetic field line, unless not until the particle hit some other particle hit on that particle that it will be perturbed to a different field line. That's why the eta is important for this the finite conductivity is important for this term.